We have to be isolated. We have to be very British.
Sí, te voy a hacer una señal en 5 minutos y luego...
No hay pregunta.
Okay.
Doesn't PhD?
All right. Well, I was hearing just outside that pretty much you're experts in optimization. So my problem or my research is not mainly focused on optimization, it's mainly focused on aerodynamics for aircraft engines. Although I'm using an optimization model to optimize parameters, but I'm not an expert on that. So basically, well, I come from Cranfield University, and I belong to Aerospace Transform Manufacturing School. And today I'm going to present you the transonic, well, the optimization, multi-point optimization for transonic axial flow compressors, basically to optimize the blades there, and to optimize it in 3 dimensions. Very quickly, it's going to be the agenda with.
It's for you.
So not only broadcasted, but also. Okay, anyway. So I'm going to present the aim of this, the objectives of the research, then the global. Then the global impact of my research, also the impact in Mexico. Then I'm going just to briefly talk about the transonic compressors to have an idea of why we're using this in aircraft engines. And then the current work that we're doing, some preliminary results and final conclusions. So, well, the purpose of this presentation is just to show you an overview of the thing that we're doing in the Center of Propulsion at Cranfield University related to propulsion and aerodynamics, specifically in the gas turbine engineering group. How many are you related to aerodynamics?
No.
So yeah, as I mentioned, the scope of this research is basically to design a framework to optimize transonic axial flow compressor rotor blades in 3 dimensions in order to maximize efficiency and also to widen the operating range. So, well, for those of you that are related to aerodynamics, you know that it's a compressor. So I'm not only optimizing the compressor, but also the fan. So whenever I talk about compressor, also having in your mind the idea of the fan, because to my end, they are basically going to increase the pressure. So at the end, I'm going to optimize the blades just for these 2 objective functions. Okay, let me just give you a very brief overview of what is this plot. So if you go to buy, or if you want to buy an aircraft engine, normally you will look into the specifications, and this is what they are going to show you, the efficiency of the aircraft engine. In this case, this is the compressor map, because we're looking just to a single component. And so basically, they are going to plot efficiency against the mass flow rate that is passing through the engine. And they are going to show the efficiency for different speed lines, for different set of throttles. The throttle is going to be basically calibrated by the pilot. So the objective of my project is basically, 1, to increase the fidelity of the flow solver that is going to analyze the flow solution across the engine. We're not using CFD, for those who are thinking that I'm using CFD. Later on, I'm going to explain why. And also, we're going to implement the multi-point optimization strategy. And then we're going to verify just few points against CFD. So basically, the global research impact is going to be that, well, you know that nowadays the aircraft industry is demanding lightness and compactness, basically for savings. And then as a responding solution to this need, transonic compressors are being used. Later on, I'm going to explain why transonic compressors are much lighter and also compact. So basically, transonic compressor can increase, if we basically optimize the efficiency of the transonic compressors, they are going to represent fuel consumption, lower fuel consumption, and then having fuel cost savings, and also less polluting emissions in terms of carbon dioxide and NOx emissions, and also other particles. The impact in Mexico is, well, basically, you know that the aerospace industry is growing a lot there, particularly in Querétaro, Tijuana, and Mexicali. Specifically for aircraft engine components, design and analysis. And in general, the aviation companies in Mexico are basically divided in assembly, manufacture, wiring systems, electrical systems, also fatigue and fracture analysis through finite element methods, and performance analysis. However, nowadays there is no research work there. No? Now we're moving towards that direction. And in fact, in Querétaro, they're going to build the new Aerospace Research Center, which is a collaboration between CDESI and CONACYT. So taking advantage of this, basically we can introduce aerodynamic analysis and research to attract foreign investment and new companies, and then we'll build collaborations there. So transonic compressors or fans, which basically are going to make the same operation of increasing pressure. They are basically, they have gained attraction because they have a high pressure ratio per single stage. So in that case, you don't need a lot of stages to have, I don't know, 5 or 6 levels of pressure ratio. In this case, we're reducing the engine weight because we're reducing the number of stages, and also transonic compressors, they don't need to be so long in terms of the length of the blade. So we are decreasing the diameter, and in this case, both things, engine weight and size. If we manage to do that, we are also going to decrease the cost of design, manufacture, because then we don't need to manufacture many blades, operation, and maintainability. Normally, nowadays, the efficiencies of these transonic compressors are between 83 and 90%. So you can tell that they are pretty efficient. However, a small efficiency increase will represent significant fuel savings. The pressure ratios of these high single stage pressure compressors are around 1.7 and 1.8 per stage. And notice here that in the first stage, we're going to have supersonic flow. That's why we have transonic flow, no? Because just in the first stage and only in the tip of the blade, we're going to have supersonic flow. And for the rest of the blade, we're going to have subsonic. And downstream of the blades, we're also going to have subsonic. So the combination of supersonic and transonic and subsonic is going to give me the transonic behavior. And also the Mach number that is basically achieved there in the tip is 1.3. So you may know that when we have supersonic flow, we are having shock waves. So that's actually the purpose of transonic compressors. Apart from the work that the compressor is going to make of increasing the pressure, the compressor is going to take advantage of the shock wave to increase the pressure. Let me do here stop, and I'm going to talk a bit about, well, this is an example of transonic compressor. It's not the normal shape of a compressor that you look. And I'm going to talk about subsonic flow. What is happening in subsonic compressors? You know that the flow inside of an aircraft engine is highly complex, three-dimensional, turbulent, and highly viscous. So we are going to have all these interactions in between the blades. Here are the blades. We are going to have basically 2 types of losses: profile and secondary losses. The profile are basically boundary layer separation, and secondary losses are leakage from the flow that is going in the tip and that is going in the vortex. However, when we have transonic compressors, also the shock the shock waves are going to introduce losses, which are shock losses. So everything is not very nice about having shock waves. No? Also, they're going to introduce some efficiency detrimental. 5 minutes. Anyway, we have 3 types of shock waves. And basically, they are going to represent, or they are going to result in 3 different behaviors. So at the moment of increasing the fidelity of my solver, I want to represent these shock behaviors. Now I'm going to talk about the 2-dimensional blade shaping that we're carrying out. Basically, when I say that it's 3-dimensional, we're only going to modify 2 angles. The sweep angle, which is in the meridional plane. So if you look to the engine, it's going to move forward or downwards. Or if you look to the engine from the front, you can also tilt it, right? So this is the lean angle. So these 2 variables are the ones that we're going to optimize. For what? To maximize efficiency and to widen the operating range. And you can see here that we have all this design space for exploration. This is the idea of forward sweep and backward sweep. Also, if you look from the top to the engine, we can move the blades negatively or positively. And at the end, and also we cannot only move the whole blade, or also we can move every blade profile section independently with different angles. So at the end, we're pretty much going to obtain this kind of shapes, very complex shapes. For example, here you can see that is somehow twisted, the blade. So here the blade profile sections were swept downstream, then they were swept upstream, and again downstream. And tangentially, they were positive, negative, and again positive. So that's basically the idea. What we're doing. We're not using CFD. We're not using CFD. Why? Because for optimization, you will need to run several times the solver. So you know that CFD takes a lot of time and high computational cost. In this case, we're using streamline curvature methods, which basically are much more cheaper. For example, one single point of analysis, instead of taking 1 week, will take just 5 minutes. So the full compressor map that I show you, I can analyze it in 5 minutes, while in CFD, just one single point will take me 1 week. And basically, this is our solver that we're using, that we're developing. And now we're in the stage of introducing, well, we have introduced the geometry definition to consider the sweep and lean angle. And now we're in the process of including the flow division models, also the shock loss model to represent the shock structure, and the other 2 behaviors that are as a result from the shock wave interaction. In a general form, not in an expert form, this is optimization strategy that we're going to follow. So, coming from an initial rotor blade geometry, we're going to analyze it first in our flow solver. Then, if we basically achieve these 2 constraints or these 2 objective functions, then it's enough. If not, the optimization algorithm is going to decide for new parameters, and the process is going to be repeated again. That's why we need these streamline curvature methods. This is what we have achieved so far. So in this case, well, this is one blade that we moved backwards at these 2 points, and then the tip was moved forwards. And you can see again the compressor map in terms of efficiency. In black, you can see the baseline geometry and see that the optimized geometry is basically generating 1% more of efficiency, which sounds pretty small, but that's enough. Right? Also, in terms of pressure ratio, we are increasing the pressure ratio by 0.2%. And, well, basically that's it. Conclusions, basically the transonic compressors are the new technology, and the advantage of streamline curvature method over CFD, and that the optimization of transonic compressors can reduce fuel consumption, and then we can point towards a sustainable aviation. That's it.
Okay.
Have you? I know you haven't done well. You haven't used CFD in order to do this, but your approximation model, how well does it compare with you?
Against,
Like against an experimental setting?
against experimental results, it's pretty much good. Yeah, pretty good match. You have only deviations for cases of 100%, and if you go to, for example, to this plot, you are only going to have deviation against experimental in this point, at the limit of the operating range, and also at this limit. Why? Because then we have there a non-steady behavior. But throughout all the curve, the behavior is quite steady, and we don't have any transient behavior. So here it matches pretty good. Yeah. Only these 2 points.
Super, very quick question. What does CFD mean?
Computational fluid dynamics.
Thank you.
How can you modulate or set the different velocities flowing on? Do you remember you mentioned that you have supersonic flow and two others, right?
Mm-hmm.
In the turbine, I think. How can you set these different velocities in the turbine?
Basically, the speed, the air speed is going to be determined by the aircraft. So the aircraft is going to input the incoming velocity. Mm-hmm. So at the moment that the airflow is going through the engine, it's gonna experience a reduction in area.
So just because you are narrowing.
It's because you are narrowing basically the compressor. You are compressing the compressor, and also because of the intake, you are also forcing the flow to increase the velocity. Mm-hmm. So in this case, we can obtain supersonic flow at the tip of the compressor, of the first stage.
Okay.
It's Rolls-Royce or GE working along with your university or something like that?
Yeah, Rolls-Royce. So I'm not only doing this kind of work, we are doing also some other studies for Rolls-Royce.
Which kind of engines you're working for?
The RB211 and the Trent
1000?
10,000.
Yes.
I was wondering if it could be applied to any other design that involves any other fluids or shapes or materials.
In terms of what? In terms of optimization or in
Yeah.
terms of the solver?
Both.
Both. The solver has proved to be pretty robust. Actually, that's an area of opportunity because streamlined curvature methods they haven't been applied in other areas than in aircraft components. So yeah, it will be nice to test it in another kind of fluid mechanics area. And in terms of optimization, yeah, why not? You can also apply that same structure and that same methodology. Because you want to improve or you want to optimize some parameters. So whatever you want to optimize, you're just going to put it there in the strategy.
Any other question? No? Well, let's think again. Very good timing. Thanks a lot, guys. So now, because I don't think Ricardo Velasquez is here. No? You're not. Okay. So we should go with Leslie.
So you will just go for coffee.
Yeah, exactly. How do we know the link
No, y es que bueno, se te hace todo tan fácil traerlo en el celular, pero no sabes qué implicaciones. Estás arrastrando de traer todo en el celular, tus cuentas, tu banco, bla, bla, un montón de información que dices, ay, ¿quién no? Pero de repente sí puede pasar algo.
Okay.
¿Cuál es el láser?
Creo que es el 9.
Y da para atrás y adelante.
Okay, this time is for Omar Alejandro Velázquez, Ortiz, with engineering applications of earthquake early warning systems. Right?
Yes.
Okay.
Okay, hello everyone. My name is Omar Velázquez. This morning I will present my PhD project, which focuses on the engineering applications of earthquake early warning systems. So this is the outline of my presentation. First, I'm gonna provide a brief definition of earthquakes in order to understand the concept of earthquake early warning systems. Then I will talk about my PhD project, the engineering applications of these systems, and finally I'm gonna provide some concluding remarks. So what's an earthquake? An earthquake is a sudden release of energy in the Earth's crust due to faulting or breaking of rocks. As you can see in the image, this energy dissipates from the epicenter as waves, through waves. So there are many kind of waves that we can identify during an earthquake. However, for the purposes of earthquake early warning systems, we will only focus on primary waves and secondary waves. The main difference between primary waves and secondary waves, as can be seen here, is that P waves travel faster than S waves. However, S waves are more damaging than P waves. When we feel the earthquake, what we are actually feeling are secondary waves. The primary waves have already arrived to the point wherever we are, but when we feel the shaking, what we are feeling are secondary waves. So this is very important in order to understand the concept of earthquake early warning systems. So we have we're in our site of interest away from the epicenter. So based on the difference between the propagation velocity of P waves and S waves, earthquake early warning systems are able to provide a warning time to know the arrival of S waves. And this time ranges from seconds to more than 1 minute. In addition, these systems are able to provide a probable location of the epicenter of the earthquake and the intensity that we are going to expect at our site of interest. So in order to make this a bit shorter, the earthquake early warning detects the P waves, immediately provides a likely location of the earthquake, the magnitude we're going to expect, and because we usually earthquake early warning systems work in networks, we can provide lead times for different locations around the network. And then we can provide alerts in order to perform safety actions. I'm going to talk about it a little later. So currently there are earthquake early warning systems already around the world. In the gray color, we can see countries like Greece and South Iberia that are working on them. They don't have the information already. They don't provide information. In black, we have countries that have earthquake early warning systems, but they only use the data for research. They don't provide information to the public. And we have, in pink, countries where the warning is provided for research and for the public. As you can see, Mexico is one of these countries. So I'm going to explain a little bit how, given that this is a Mexican symposium, I'm going to speak a little bit about the earthquake early warning system in Mexico. So I think okay, this is just a video of the earthquake in Mexico. I think everyone knows about, well, the Mexicans here know about September 1985. One of the major disasters in the history of Mexico occurred. It was a magnitude 8.1 earthquake that had consequences around 10,000 deaths and 30,000 injuries. So after this massive and destructive event, CONACYT and the National Institute of Researchers in 1986 proposed the idea of Mexico having an earthquake early warning system. So in 1991, Sistema de Alerta Sísmica, or Seismic Alert System of Mexico City, which is called SAS, was deployed. During the first experimental period, 80 earthquakes were detected in advance. This is the first system in the whole world that disseminated information to the public. And one remarkable characteristic of the system is that 10 years after the massive earthquake, 1995, it provided a 72 seconds alert for a 7.3 magnitude earthquake, which is pretty considerable. In 2003, the state of Oaxaca, one of the states that is located in the highest seismic area of the Mexican territory, launched SASO, an updated version of SAS. And recently, SAS and SASO joined forces in order to create what is called the Seismic Alert System of Mexico, or better well known as SASMEX. SASMEX started with 49 seismic stations around the southwest coast of Mexico. In 2010, the Mexico City's government decided to give some money in order to improve the network, and 64 stations were added, giving coverture to all the southwest area of the Mexican territory. And I would like to ask something to you guys. The Mexican people here, can you raise your hand if you knew about SASO or SASMEX, please? Okay. Because a big problem that the system is currently having is that the number of users that have access to this information is very low. The system looks very nice, but the number of users that we have currently is, well, that they have is very low. And the people who have the system, or who have the access to the information, lack of an integrated response with local or federal government. So I received my warning, but then what do I have to do? Where do I go? Where do I run? What do I have to do? So the purpose of my PhD is not this. This is just a brief overview of Mexican system. This is just for you to know what's happening in Mexico. What I'm doing, well, these are two examples I want to show of how early warning systems are provided. I can show them to you later because the videos aren't working. So let me see. Sorry, I can show them to you later. So my PhD, Engineering Applications of Earthquake Early Warning Systems. So we will basically design two different methodologies. The first one is the design of algorithms able to stop mechanical activities automatically. Basically, for example, we will focus in trains, elevators, and dangerous machinery. And the algorithm will be as follows. We have the event, the earthquake. The earthquake early warning system provides the information of the earthquake. We trigger an alarm, and we will develop control actions in order to stop trains, lifts, and dangerous machinery. So people can perform some actions, look for shelter, and be safe. So this is what we're gonna do. However, given that all this process is probabilistic, we have many uncertainties involved in this process. So it's very easy to trigger false alarms, and we don't want to do that because they cause unnecessary losses and disturbances. For example, if we stop a power plant, it's not just that, okay, I did a mistake, I need to, sorry, you can start again. It takes 3 weeks more or less to restart the works in a power. We are not going to allow that. Our systems cannot allow an I'm sorry, it was a mistake. Okay. This is the first part of the methodology. The second one is a bit more technical. I hope you can understand me. I'm a civil engineer, so this is what we're actually going to do. We're going to design an algorithm for semi-active structural control systems. So what is this? In order to understand this, I need to give you three important concepts. The first one is structural damping. Structural damping is the natural ability of structures to dissipate energy out from the building. That's natural. The second one is natural stiffness. The natural stiffness is the capacity of one structure to stand forces and deformations. And the last one is the natural period of a structure. If we think about a pendulum, the natural period of the pendulum is the time that it oscillates from one side to another. So if we put the pendulum backwards, we can think about the building, and the natural period of the building will be the time that it will oscillate from one side to another. So with these concepts introduced, what we're going to do here, the second methodology, is the control of the dynamic characteristics, stiffness of damping of a structure in real time in order to improve the seismic behavior of the structure with the information given by the earthquake warning systems. I know that this sounds a bit too much, but I'm going to explain you. So we're going to use what we call semi-active variable stiffness systems at magnetoological dampers. From now on, I'm going to say MR dampers because this magnetoological thing sounds a bit hard. And I'm going to explain what's magnetoological. It's a bit of a hard word. So this is a video as well, and I really wanted to show this one. Come on.
Oye, ¿y si lo ponen, no?
Okay, I can show you the video after as well. I hope you can understand me. So let's think about a plate with oil. The oil used for cooking with small particles of iron. Okay. So if you think about, if you spray it with a spoon, the thing is it's not viscous at all. But if we apply a magnetic field, the viscosity of these fluids increase significantly, very, very, very high. And this particularity is used in MR. These are MR fluids. We use MR fluids and MR dampers in order to add and increase damping and stiffness to a structure. I hope that was clear. The video is amazing.
You have them on YouTube? Or?
Yes, I can show them if I'm not.
There is internet, no?
It's not going to take a bit too much the presentation, so I can show them the videos after all of them. So again, MR dampers are devices able to dissipate mechanical energy out of the building, adding stiffness or damping. And this is very important. They use low power electrical currents. This is very, very important given that during an earthquake, we cannot rely on electricity. We don't know if there's going to be a cut. So the battery I'm using for this thing right now is more than enough to activate an MR damper. So that's where there are semi-active and passive dampers. If you are interested and you would like to know about them, we can have a chat after. But again, like in the trains thing, we want everything to be fast and automatic. We don't want anyone in a computer or anything like that. So the process we're going to follow for this second methodology is as follows. So the earthquake early warning system will provide information from the earthquake, and we can estimate a probable accelerogram of the earthquake coming. Okay, this accelerogram is transformed into a tool we use in earthquake engineering that is called elastic or inelastic spectrum that correlates the acceleration that the earthquake coming can provide to the building with natural different periods of buildings. The natural period I just defined before. This is a bit more clear in this slide. So we have our building. We have the elastic spectrum, which is the transformation of the accelerogram to an engineering tool. According to the natural period of our structure, we come to the graph, we find the period, we go to the vertical axis, and we can find the estimated force that that the building will face. So the important thing about the MR dampers comes here. As you can see, the graph has different values, but it has peaks. Let's say that our structure has a period of 0.25 seconds. The acceleration or the force that our building will face will be, this is 1.5 G, G is 9.8 meters over second square. Probably that's not like a very big number, but that's very, very huge. So what we're gonna do with MR dampers, the natural period of a structure is based in the stiffness and the damping of the structure. If we add stiffness or damping to the structure, we can then change the period in real time before the earthquake comes. So if we have a period of 0.25 and we are here, we can we can move the behavior of the building, so we can find lower, probably not this, that would be desirable, but lower peaks, less force to improve the seismic behavior of the building, and hopefully we won't have damage in the building. This is not as easy as it looks. It's not like I say, like you just move here your building. There are many things that are involved, but for the purposes of this talk, I'm just going to focus on this. So the last part, we find our force, and in order to improve the seismic behavior of the building, we go into a very complex algorithm that transforms these forms into voltage, the voltage necessary to activate the MR damper, and then add stiffness and damping to our building. The more the electricity current, the more damping we create, and then it's a real-time thing. We can play. We want this method. It's done in milliseconds. I think I don't really remember. I think it's 15 microseconds. Everything is very, very, very fast. So if the earthquake happens, let's say where Oriana is, and I'm the building, and I have, I don't know, less than 1 second to do an action, this MR damper is probably, hopefully, enough to reduce the danger. Okay, some concluding remarks. Earthquakes cannot be forecasted. We can predict them once they happen, but so far there are no studies saying that there's going to be an earthquake tomorrow at 5 p.m. That doesn't exist anymore. So we need methods to reduce infrastructure damage and losses. And we think that the earthquake early warning systems are a powerful tool that can be applied in different ways in order to reduce economic, human losses. However, the design of these methods have to be very well optimized in order to avoid undesirable consequences like false alarms. However, we can provide a very nice method, very nice results, but key factors are government participation and education of people. If people don't know how to act after a warning is provided, then it's totally worthless to have all this. And finally, I hope my results are good. All these discussed methodologies will be developed and applied for the current early warning systems in Mexico City. Thank you.
Thank you very much. Any questions, please?
How is the sensor connected to the system to receive the signal?
In the building or the one you could have?
In the building for the dampers.
It's with an antenna.
Oh, okay.
All these things are signals.
Okay.
Just radio signals, and they just from the station they send the information to the sensors, and then the sensor just beeps. I had an animation with a beep, but I can hear it.
So how costly is to implement?
Okay, the cost benefit. I didn't say this. I started my PhD just 2 months ago.
All right.
So first, I'm gonna design the algorithms, and then I'm gonna do a cost. What do you say? Cost benefit study. What I can say is that one of these MR dampers is about $2,000 which, if you compare it with the total money you use for a building, is almost nothing. But I'm sorry, I would like to answer that question. But so far, that's one part of the study I'm gonna do, and I just started 2 months ago.
So it's 2,000 for the whole system.
No, one damper.
For one damper.
I'm talking about the dampers in the building. The earthquake early warning system, that one that receive the.
No, yeah. That's.
Yeah, for those ones, we won't actually buy like a sensor. We're gonna use data from the earthquake early warning system in Mexico City.
Yeah, you just plug it in.
Yes.
For that.
We won't buy anything.
Okay, quick one.
Yeah, just which one? I know you've already just started, but would it be easier to design the buildings with to do this, or it's better to just design whatever the architects just designed it as it is,
depends.
And then
Currently, seismic design of buildings is implemented all around the world, but what about the buildings were already constructed?
Yeah.
We can apply them to them. So the best will be to to construct seismically to stand forces like this. This is carried out all around the world already. But for buildings that are already constructed, we need to implement, that's what I said, we need to improve the seismic behavior of the buildings. There are many methodologies. We just came with the idea of very one systems.
Yeah, but that means you have to change somehow the structure of the building or accent.
Yes,
right?
but I didn't show how many.
I mean, not just plugging a sensor and then the building will
The
do
MR
itself.
damper is something like this that you attach to columns, beams, or the structure, and then you input stiffness and damping. Yes, it's not just only a sensor that sends signal. No, it's mechanical.
It's like having
Sorry,
an
I forgot
Yeah,
to
so
talk
I
about.
think one of
And
the
the-
major costs will be someone actually dig to the base of every building and put those things.
No. Imagine the column you are just sitting next to. You just like kind of plug it
Yeah, but then you have to plug it at the
No.
so in every floor.
in every floor. According, it needs an study. It needs analysis. So we played first in softwares. We add different positions, different dampers, and then we come with the best result.
You make like an scanning of the performance of the building, how it behaves in the movement, and then you plug the dampers to make it to aid
With these softwares, you can check exactly how a column is behaving in real time, in microseconds and fibers, and very complex.
I think
Yeah, it was pretty much related to that. So considering the structure of a building, I know that you need to make that study, but for example, let's say for a room of 10 by 10, in a normal building of, I don't know, 20 floors, how many dampers are you going to use?
And that's something I cannot answer.
Or more
Also cannot answer, sorry.
estimation?
Well, usually they add them, as he said, in the connection of the structure with the foundation. So let's say that we have in that building 10 columns. Right now I will add one in any one, but it's something I just saying right now.
And I guess also it depends on the material. If it's
Yeah,
marble or
it's steel structures, concrete structures, masonry structures, timber structures. So there are plenty of things we have to check.
I just want to
Sorry, we don't have time. Sorry.
like a final.
Yeah.
It's not actually a question. It's just like a final remark to this.
Okay.
Like there has been sociological studies that prove that 50% of the guilty on a disaster is because people is quite skeptic on the tools you are using. So if you have a seismic alarm, the skepticism of leaving that alarm is costing you valuable seconds to react. So the first part of any kind of these PhD projects should be also address how to spread that these systems are reliable before just implementing them, so you can like literally educate people on this matter.
It's a key factor.
Yeah, exactly.
This won't work if people are not educated.
They tweet about it first.
Come again?
They tweet about it first, and then they
do it about.
Yeah, until it's in Facebook, then you really.
But I believe it's very important because currently it's like there's only like one alarm, seismic alarms, practicing only on September.
Okay,
Once a
I
year,
asked
no?
how many of you know this, but how many of you have had access to the seismic alarm,
Data. No.
to the warning? Nobody. How many of you are from Mexico City? This is in 1986.
Yeah.
When I was born, and I had no idea just 2 months ago when I started my PhD.
Well, there's Skylert.
Yes, but Skyler is not. It's something a bit different. It's not from the Mexican. I'm not sure, but I think it's not.
Linked.
From
It's linked with Mexico.
Okay, it's
right
linked,
now.
but
So,
the,
but people is trusting now more in Skylert rather than in the SES.
that's what I showed with red letters. What's happening, because it's, for me, not ridiculous, but I cannot believe it. It's a it's one of the best networks in the world, and we have some of you have. But yesterday I was asking, and one girl from Oaxaca who they have Sasso, and she was like, "What's Sasso? It's food or?" They have no idea.
No, the problem with that is that we were working with some of these things we're playing, but in the outskirts of Sinaloa, they put a lot of these bubbles. One day the Navy went and put these bubbles just to check the earthquakes. The next day they were
Well,
overnight the
again,
pillars, whatever. They just took it because they thought that they were spying.
This is a key factor, education of people. So if you put sensors on people that steal them.
Okay, we have to finish with that.
Thank you.
Let's take the next María, ¿están los presentaciones? María Vanessa y María.
Sin apellido.
Goyarzo. Así es el apellido.
¿Cuál es su
Good morning, everyone. We are Marisa Muñoz and Mariana Goyarzu, representing the University of Nottingham. We're going to present you our project of a residential function in the cold climate of Astana, Kazakhstan. We participated in the Iceberg Multi-Comfort Student Contest, representing the UK in the final stage in Astana, Kazakhstan this semester, and we're going to present our project.
So first, an introduction to the project. Astana is the capital city of Kazakhstan, and the challenging for this project was due to the extreme climate conditions, because this city has 40 degrees in summer and minus 50 degrees in winter. The project will be located within the Expo Astana 2017, which is an exposition that is sustained by the government to promote the sustainability and renewable energies. And here in the master plan of the project, we can see this part here in red. That was the site for the project. It's around 3 hectares. Has an area of 3 hectares.
The concept: human beings through the ages have been able to adapt to the environment around them to achieve thermal comfort. This is no different in Kazakhstan, even with their extreme climate. But in today's, we have to work with thermal comfort, providing for the user, but as well taking into account how much energy are we wasting on having this thermal comfort. In the past, people used to have thermal comfort without having AC systems. So with all the new technologies, we achieve a range of thermal comfort in our buildings, but the energy consumption is very high, specific in these cities that we need heating as well as cooling during all the year. That's why our project includes passive strategies that are incorporated before the design of the buildings, and as well renewable energy that is to fulfill the energy consumption of these buildings in order to have thermal comfort. So our principal objective was the user, providing thermal comfort for it. So we have to study the environmental climatic conditions of Astana. Winters is the worst period of here. We have almost like 6 months of winter with really low temperatures. And one important factor is that it has very strong winds. So with low temperature, you cannot even walk outside. We have talked with people from Astana. We were there in May, hopefully. Luckily for us, it was summertime. But they were talking to us that you cannot even stop the car engine. You cannot walk to the bus stop because it's horrible. So our project is 10 buildings within an area. We located where the strong winter winds come, and we are proposing an earth slope used to redirect the wind, giving comfort to the user on a ground level, and as well harnessing the wind energy with wind turbines for the renewable energy. Another aspect is that we are having our compact design for the buildings in order to preserve the heat inside of it, and also harnessing the sun's radiation so we can have, with the proper orientation, sunlight for all the bedrooms in our apartments. Another very important aspect of our project itself is that we are connecting all the buildings within the complex in an underground level, having corridors for social interaction, and as well we have a corridor pedestrian network that is closed so that people can walk between the buildings and the service areas without having to go to the outside, and even especially for winter. We are also using some passive strategies incorporated into the building and working together with the courtyards and the environmental landscaping to provide thermal comfort with a low energy consumption.
So the project layout, design was based in basically 5 main features. This is the first one, and here we can the project have an underground level for cars, so there is no vehicles roads on the ground level. So here we can see the underground access, as well as a parking lot area for visitors. There's a ramp, a pedestrian ramp to the air slope that Marisa was talking about, that has a viewpoint that connects the project with the Expo Astana, that it was located here, and the city of Astana, that is here. And for the safety, each emergency staircase of the buildings connects to the pedestrian paths that are also that can be also used for emergency vehicles. On the underground level, we have all the paths and roads for vehicles and bicycles, as well as parking areas, and the underground corridors network for pedestrians, as well as a generation plant and a wastewater treatment plant. Also in the underground level, we have the social and public areas. This is because we have open and closed, because in the summer people can be outside, so we want to also, this is also important for them to be in the outside and connect with the nature. So, and this whole network connects with the main general service building that is located under the slope that provides to all the users services and recreation amenities. Well, here is the layout and the landscape. It also has a really large, it's almost all covered by green spaces and areas, so it has a low footprint. And there's a sustainability and renewable energy system, like both the layout and each building have renewable system, passive strategies, energy efficient systems, as well as recycle and organic waste tube evaporated system. Here are some renewable system. This is like a section of the complete layout. You can see here the slope, the buildings, the underground level, and the upperground level. The building itself, here is a section of the building, and here we can see, here's a section. Here we can see the connection between the social areas. There are the atrium for indoors, the courtyard for outdoors, and the underground pedestrian network. There's also, in each floor, there's 4 apartments, depending, they're different sizes depending on the user. Each 3 floors, there's balconies for social areas, and in the vegetation, natural vegetation in the atrium is used to improve the user's health due to their quality.
Okay, in order to achieve multi-comfort criteria, which include visual, thermal and acoustic comfort, as well as indoor air quality and energy efficiency, we follow 3 steps. The first one is the basic building design. So since the beginning, we have to think about how to orientate and how to arrange the buildings in order to achieve that natural energy that comes from the wind as well as from the sun. So we ubicate the buildings, trying to avoid as much as possible within the area we have allocated, without trying to avoid shading between each building. Also, every strategy that we use, we verify them with softwares. Trying, for example, in this, we are trying to simulate how the wind is going to come and how there are the velocities. So we are proposing the air slope in order to have the air velocities in the corridors on the ground level in really low velocities. As we can see here, we almost have not wind at all because of our protection. Another very important and essential part of our project is the building envelope. So we are using, in this case, isover and Saint-Gobain high insulation materials that protects our building in order to help preserve the heat during winter and the cool during summer. The U values is how the heat transfer from the inside of the building to the outside, depending on the difference of temperature, are really low, and these are exclusive of Isoberg multi-comfort criteria that are applied into their materials. So we are having really low U values. This helps also on our energy demand of the buildings to have really passive house standards. Another important aspect is having exterior shading. So we have different angles from the sun during winter and summer. So we have to take advantage of this. We propose exterior shading so we can help prevent overheating during summer, but also we can harness the sun's energy and during winter when we need more heat. The second step is the use of passive systems. Here we can see our double facade, which is essential for our buildings. It can work in winter and summer. In winter, we have them closed, so it helps gain solar energy and keep it inside. So it's like a double skin for our buildings. And in summer, we have it open, so allowing natural ventilation, as well as it has openings on the walls. So because of difference in pressures and temperatures, the cold air comes in the low openings and help exhaust the heat in the high openings. Also, we have like the double facade and the atrium, which work together in order for the air to flow. We can see here is the winter when it's closed and in summer when it's open. We are also taking advantage of ground to air heat exchanger that we are harnessing the constant temperature of the ground throughout the year. It doesn't vary that much. So during the hot season, we can extract the hot air from outside, and with the temperature of the air, we can cool it up. So our air conditioning systems don't need that much energy because already the air that is flowing in the building is not that as hot as the outdoor temperature. And in the other countries, the same, but during winter. We use a CFD analysis for a typical summer day, just to verify the temperatures and the airflow through our apartments. And here we can see that we are within a comfortable range. And the third step, it was the use of efficient systems and renewable energy. So our double facade in all the buildings is made up of photovoltaic ventilated facade. Like the technology of today's, it's really good because we have PVs, but they are translucent and clear. So we can harness the sunlight, allowing into the buildings, but as well we are harnessing solar radiation and converting it to electricity. And we have 10 buildings and a huge amount. Both facades which are orientated toward the sun's path are made of this PV. So we have a great area of PV that it is generating all the energy consumption from our buildings. As well, we are harnessing our air slope again because it is on orientation to the south. So we are harnessing the more solar radiation. And we also have our wind turbines, that these are domestic wind turbines, not as the one that we saw out in the camp, because we have to follow the regulations because we are really near our building, so we don't want to disturb with acoustic for the people as well as for security. But even though today they're domestic wind turbines that can generate electricity, but as well having really close to the buildings. We have solar thermal collectors as well in the roof for providing the hot domestic water, and heat recovery systems in the building, because even if we have a really good design and try to improve all these passive strategies so we cannot need the use of air conditioning because of the strict climate conditions, there's going to be a point that we need air conditioning to provide thermal comfort. But with these heat recovery systems, we are helping even decrease more this energy consumption. So with all the energy consumption generated, but with all the energy, renewable energy generated, we are providing and supplying all the energy consumption. So our complex is a zero carbon emission complex which promotes multi-comfort dwellings and as well social interaction. Thank you.
I just have like 2 minutes more. Okay, questions? Yes.
Well, as you mentioned, Astana, no? Why did you choose Astana? Just because it's the most extreme city?
No, yeah. Actually, we participated. It's the isover multi-comfort student contest. Is a contest that has already been 11 years in Europe because of is the company of these high insulation materials that they are promoting the multi-comfort material. So they chose this city of Astana, especially because of its extreme climate condition and because it is really difficult to design a project that is based on 2 extreme climates, because usually you have or a really bad winter or a really bad summer. And depending on that, you include the passive strategies that you want to use to have a low energy consumption. But in this case, we have both. So we have like to really analyze, do a really hard job to lower the demands of the buildings, because we have passive house standards that even in a temperate climate is really hard to achieve. So that was the challenge of this contest. This is why it is in Astana.
And it's also because the government of Astana has this project that is like a complex, well, it's a master complex for exposition of renewable energies that is right now is actually they're building it right now. It will be finished by the 2017, and Isover is participating a lot in this exposition. So that's also why.
And how feasible is to implement this same strategy, this same ideology in other?
Very visible. It all depends on the location of the project, but like all these strategies, passive system, energy system, can be applied.
Yeah, it depends basically. For example, right now applying it to Mexico or to the European Union, because these, for example, isover materials with high insulation right now in the market of the European Union, it's really have really competitive prices because there are a lot of companies making them, and also the government is going to give you subsidies. And for the 2050, they have like this zero carbon emission trying to promote and everything. So it is more feasible economically. But for example, trying to apply them to Mexico, there have been even studies made in social housing that if they apply this high insulation for the passive house, having the payback period with the energy and how the costs are going to be increased and everything, if they were right now available, all of them with a competitive price, it will be feasible. But even if right now it's not that cheap to get them in Mexico, if you have a good investment, because the investment is the great, but with a payback period with the low energy consumption you have, so at the end it is really feasible. It just has to start incorporating in the way we build our buildings.
I can say in your project the cost of the maintenance of the whole system, because I know it's like lots of photovoltaic, the wind turbines, heat system. Is it something that you're considering in the cost?
Well, this project was mainly for a styling competition. So basically, they gave us certain like guidelines, and the cost was like not.
Not a constraint.
Yeah.
Okay.
Yeah.
So
Yeah.
basically,
So we didn't like make a budget for or a payback period for this.
Okay. Yeah, because I'm thinking like, yeah, you're saving a lot in energy consumption, but like zero emission is quite self-sustainable. But what about the cost of maintenance?
Yeah, especially right now in Astana, what they are trying to do. Astana is the capital city, but 10 years ago it was another country, another city. So they are having a lot of investment. So this expo is about all renewable energy. So the most you have of renewable energy, it is going to connect it within all the complex.
Okay.
So at the end of the day, it is going to be visible, all the initial cost with all the energy that you are generating.
Okay.
You don't have to build this. You have the money to build this and then to sell them. Would they be luxury items, or would they be something that
Social housing.
Yeah, exactly.
Well, the design of the building are based on standards, also like standard measures. So it can apply for like a lot of different type of material. So we can, depending on the buyer.
The real budget.
Yeah. We can adapt the building for different type
But in
of.
order to achieve like this, like because it's fantastic, right? It's like zero emissions and everything. But that implies that in order to get that, I think like those gonna be like super luxury, like a super luxury complex
It
to
doesn't
achieve
have
all this, right? Because
It doesn't have to be. I mean, it is. Actually, these are meant for an area of residential, but they're near to the university. And the buildings and everything, like, it doesn't have to be that expensive. Like, it doesn't have to be. It can be, depending on the materials that you're using, like on the insides, but it doesn't have to be.
But I guess in the long term, the cost benefit analysis will contribute to
Yes,
to the
of course.
Especially because right now you have the government financing all these expo. So actually, if I don't know if you can recall the size of the apartments, they are not that big. Like if you're going to pay a lot of money, you have small bedrooms, small kitchen, everything, because it is designed for the typical apartment that is used right now in Astana. So what the government is trying to implement is trying to build all these, but for the people that is working in Astana. So it's not the luxury. There are some another apartments that are right now in Astana, like these developments are kind of luxury, but this, especially of Expo 2017, what they are trying to do is like create this new city. So thanks to Astana's government and the money that is financing, you can give that kind of project. Actually, this project, not our project exactly, but the site is special for residential function. And one of the principal objectives of the contest, we were 50 teams from all of Europe. So it was an idea concept. So they are going to, the people that are working on the expo was on the contest, and they saw all the presentations, and they have all our project information. So they are going to try to incorporate all of it. So in 2017, we'll see a residential that is going to already be built, and it will include all renewable energy. So they have the money to make it feasible for the people, because the initial investment is by the government. So it's what costs the most. So people who are going to live there, their energy bills are going to be really low. So
But here are the different size of apartments. Like we are providing different range. Like maybe you want the smaller one or the bigger one. Maybe you don't need a big apartment because you're just one person. So it has these like different types. Yeah.
Okay. The only thing that is not clear is it your entire design? I mean, the whole layout of the buildings and the specification, or you got at least some, I don't know, some rules that it has to be at least 10 buildings and it has to have 10 floors.
Yeah.
They give the density from the gross area. So we cannot make apartments more big because we have like an area of the building and the people who has to live there. And the size of the layout, So that basically were the two things that they were like, okay, you have to follow this. We need the height of the buildings. They have to be 8 stories
as maximum.
So
and like we kind of have those.
We need to fulfill the requirements of the competition. So we have standardized projects within all the projects.
Were there other students involved? Because I mean,
in this one of our friends, he's from Ecuador, so we were the 3 of us. They are architects and I'm a civil engineer, so we work together.
You need different skills.
Yeah.
Lay out the buildings and the
But no, it was a lot of work.
But it was for the perfect, like, cause the 3 of us, plus we're studying the same master that is sustainable building technologies, so it was the perfect.
We incorporate all of our classes, subjects, and our backgrounds as well.
So was this only one module? Like
No, this was
contest.
not a module. This was our holidays.
Yeah, it was our contest. So our prize was going representing the UK, paid by our university, to Astana, Kazakhstan, a totally crazy city. So
Yeah, but we like invest a lot of time doing this project. Like
yeah, because
it
we have
was
to
a big
plan it
one.
since scratch, and then trying to fulfill the requirements that are for cooling and heating, less than 20 kilowatts hour per meter square.
Plus all the simulations.
That's really
Guys, we have to finish here. Let's thank again to this. There is going to be same place yesterday. Do you remember?
No.
Darwin. No? Darwin. Yeah, just downstairs and we're going to prepare everything.
Grabaste
Llevo
todo.
más tiempo que no está.
Sí. En Astana, llegaba así te paras. Ese es mi equipo y nos dieron 5 minutos para presentar el proyecto.
¿Por qué no trajeron a la compañía de Ecuador?
Me está sacando la visa ahorita, de hecho, anda por ahí.
Está sacando la visa
Para viajar, la Schengen visa.
¿Siguen live streaming?
Sí, ya sé.
¿Quién está viendo?
¿A dónde van a ir?
¿Quién está a las 2 de
A
la
las 2 de
mañana?
la mañana, no tengo nada que hacer, voy a ver
¿Pero a
el
dónde?
Symposium.
No, a lo mejor su familia.
Ella. Porque vamos a viajar en septiembre para su cumpleaños.
Aquí empezamos a decir maldiciones que
No, yo pensé que iban a viajar a presentar